Hi, in this video I'll be talking about some miscellaneous topics with radicals and exponents that are all kind of coming out of the same chapter, but not all from, I kind of put different sections together. A lot of this you've seen before, but I just want to make sure you know it. So when we're taking a root using the radical like this, we're undoing a power. And some of these are harder than square roots. If I were to ask you to do one, there's an assumption that there's an easy answer. So for example, the third root of 64, we're basically asking what number raised to the third power gives us 64? And you can check that that's 4. If I'm giving this to you without a calculator, you can assume there's a nice enough number. Fifth root of 32, well, we're thinking what raised to the fifth power gives us 32. You can check that that's 2. And similarly, what number raised to the fourth power is 81? That's 3. And a really important thing to notice is that when we're dealing with positive numbers, radicals and powers of the same index will cancel. So the cube root of z to the third is just z. Cube root and cubing they cancel each other out. It's like adding 5 and subtracting 5. So in a problem like this, you might be really intimidated and think, well, gosh, what's 38 to the 7th? I don't want to figure that out if I don't have a calculator. But the 7th root of that, by just the cancellation, would have to be 38. Power of 7 and 7th root cancel each other out. Now, sometimes we'll express a radical using a fractional exponent. 1 over n just means the nth radical. So for example, 9 to the 1/2 means the second root of 9. That's just the square root of 9, which is 3. 27 to the 1/3 means the cube root of 27, also 3. The 1/4 power of 10,000 means the fourth root of 10,000. We're asking which number raised to the fourth power gives us 10,000. And that's 10. So this is definitely worth knowing. In future math classes, it will be really helpful if you can rearrange things to use exponents instead of radicals. Now, a couple of rules involving exponents, and let's really break these down. X squared times x to the fifth. Well, x squared means x times x. X to the fifth means x times x times x times x times x. And when we multiply all this together, we get x times x times x times x times x times x times x. We have 1, 2, 3, 4, 5, 6, 7 of these. And what we're noticing is that there's actually a predictable rule. We started with a second power and a fifth power and wound up with a seventh power. This is not something where you would have to write out all those intermediate steps if you understand that pattern. Similarly, x to the 8th over x squared, if we had to write this out, it looks like this. 2 x's up top cancel with 2 in the bottom, and we're left with 1, 2, 3, 4, 5, 6 of them here. You can probably figure out the general pattern if we started with powers of 8 and 2, where that 6 came from. X cubed to the second power means x cubed times x cubed. That's x times x times x times x times x times x, which is also x to the 6th. You can probably guess where the 3 and 2, how the 3 and 2 combine to give us that 6. So we have some general rules here. Assuming the bases are the same, a to the b power times a to the c power. Right? Note same base, otherwise this won't apply. This is a raised to the power b plus c. That's what we did in the first example on the previous page. When we're subtracting a to the b divided by a to the c, when we're dividing, we're subtracting the exponents. And power to a power, we wind up multiplying those. And these rules apply even if we have fractional or negative exponents. So we'll see some examples. This right here would be x to the 2 times 5, which is x to the 10th. This middle one is y to the 1st over y squared to the 3rd. We can subtract. That's y to the 1 minus 3. So one way of writing the answer is y to the negative 2. Another way of looking at this is it's y over y times y times y. And these cancel. This is the same as 1 over y squared. These are the same. Sometimes we'll want to express something using a negative exponent. Sometimes we'll use a fraction. So this is worth knowing as a rule. Over here we have a lot of weird stuff. So in the numerator we can use the rule that says bases are the same, I can add those exponents. 1.2 plus negative 1 is 0.2. And then for division I can subtract 0.2 minus 3.8 is negative 3.6. That's a very awkward expression, but that's our simplified version. Instead of having 3 different exponential expressions, we have just one. And now our last page, just covering some of these rules. If we have an exotic exponent, we can figure it out by combining things we know about fractional exponents and other things. So 8 to the 2/3. I'm going to write 2/3 as 1/3 times 2. And then I'm going to say that's the same as 8 to the 1/3 to the 2nd power. A fractional power like that is a radical. So this is the same as the cube root of 8 raised to the 2nd power. The way you might want to think about this is that the numerator here measures the power. There's a 2nd power involved. And the denominator measures the root. There's a 3rd root. You can do them in either order. You can square and take the cube root, or you can take the cube root and then square. It's usually easier to do the root first. Cube root of 8 is 2. 2 squared is 4. So let's look at these. 9 to the 3/2. What that means is we're doing a 2nd root, a square root, and a 3rd power. So this is 3 to the 3rd, which is 27. 16 to the 3/4 means a 4th root to the 3rd power. The 4th root of 16 is 2, so 2 to the 3rd is 8. Negative powers are the corresponding positive power, but in the denominator. Seven-sixths power means the 6th root raised to the 7th power. The 6th root of 1,000,000 is 10. I made this fairly nice. So this is 1 over 10 to the 7th, or if you want to expand that, 1 over 10 million. So you'll notice this is the rule we used. And then another rule that I just want to highlight is x raised to the 0th power is 1. You can just, there's a reason for this from the rules, but just consider this the definition of the 0th power. In some cases, if we're applying a formula, it might wind up with a 0th power, and you can just say that means 1. All right, so that's it for this video.